All right, so in the last video, we talked about the idea of chairs. So let's go and get some practice on drawing them. So here we have an example of a cyclohexane, and it has a single methyl group. Methyl is going to be our CH3, and it's attached on our structure. Now, there is some stereochemistry associated with this, and there are going to be two types of stereochemistry. We're going to have wedges, which is what we have there, and then we're going to have dashes. Those wedges and dashes are going to correspond to our directions. So you can define it however you want. You just have to be consistent. To make things easy, I am always going to define my wedge as being up and my dash as being down. If you want it to be opposite, that's fine, but the key thing is you need to be consistent. Once you say it is a certain direction, it needs to always be that direction for the rest of the problem. So in this case, we're going to have a CH3 that is going to be up. Now, before we can even put it on the ring, we got to draw the ring. And that's going to be kind of the first thing that you want to get a lot of practice on. How do we draw our ring structure? So in general, I'll kind of always do just like a set of parallel lines to start. So to start, I'm going to take two parallel lines, and I'm not going to make them even. So if I have two parallel lines, what I'm going to do is I'm going to shift it a little bit to have them be offset. So in this case, let's go ahead and draw two parallel lines, and we'll see that they're offset. Maybe make it even a little bit more obnoxious. Once you have those two parallel lines, on the side that is closer to like the in of the other one, what we're going to do is we're going to draw two more parallel lines in the opposite direction, and these are almost going to be making like almost like a triangle. Like imagine you put like two more sides, you can get a triangle. And then we're going to have two parallel lines which are going to go in and connect them. So there is, for example, one of my chairs. Didn't give myself a ton of space for the next part. And we're then going to draw the flip. And the flip is going to be very similar. We're going to start with two parallel lines, but in this case, we're going to be in the opposite direction. We're going to go and complete, or kind of like two more parallel lines, almost like make some triangles, and then we're going to go and we're going to connect them. And here from our chair flip, our two different chairs, we'll have one that's our original structure, and then one that's going to be the flip of it. So there's our two base chairs that we have, and we'll get more practice drawing those, and you'll get hopefully in a habit of being able to draw them pretty quickly. We're going to need to add our group. And let's go ahead and think about this CH3. In this case, we can put it wherever we want on our molecule, kind of like with Bob Ross. This is our canvas. We can do whatever we want with it. We can use our kind of imagination and put it anywhere. However, unlike with Bob Ross, once we put it somewhere, everything else needs to follow. We can't just keep adding more big trees and clouds and mountains all over the place. So let's go ahead and put it at this top right position. I like putting on the top right because then it will always say the right, and it has nice extra space to draw things. But you can put it in any position. If you want to put it in like one of the little armpits, you can put it wherever you want. So at this position is where I'm going to put my methyl group. And we know that it has a wedge because it's drawn with a wedge. And we've defined wedges as being up. That means my CH3 needs to be up. And there's only going to be one up position and one down position. And we need to know, is that going to be an axial up or an equatorial up? And in the ones that are kind of like pointing in this, like this is almost like an arrow kind of like pointing towards that circle, we're going to follow that same direction for our axial. So I'm going to have an axial position here, and then I'm going to have an equatorial position. So here I'm going to have an axial up and then an equatorial down. So my CH3 and then there's going to be a hydrogen on the other one, and that hydrogen is kind of not drawn, it's just understood. It's going to be my dash. So I'm going to have here an axial up methyl and then an equatorial down hydrogen. And that's going to be my very first drawing of my chair. Now what we're going to do is we're going to take it and we're going to flip it. And we're going to then compare those two different ones and decide which of those is going to be more stable. So in my ring flip, what we're going to do is we're going to take this and we're going to be pulling it down. So that now corresponds to this position here. This position, you'll see that the two lines are kind of both pointing downwards towards my dot there. So I'm going to have a downward axial and then therefore an upward equatorial. My CH3 is still a wedge, and it must remain a wedge in all of these. So we are going to make sure that it's still up, and in order to be up, it needs to be in this equatorial position. So we're going to have our CH3 here, and then our hydrogen here. So now the CH3 is going to be equatorial up, and my hydrogen is going to be axial down. And you'll notice my CH3 is up in both of those. The chair flip just moved it from axial to equatorial, and my hydrogen was down in both of them. It was originally equatorial down, and now it is axial down. So we keep the same direction. Our stereochemistry, which is defined by our starting material, all we're doing is we're putting in a different position, axial versus equatorial. And we're now going to go in and compare those two in terms of stability. Now, one thing that we want to minimize, and we talked about in the last video, is the idea of 1,3 diaxial interactions. We don't want big things in an axial position. And if I look at this molecule that we've drawn, all of these other positions, so for example, way over here at like this position, there is an axial down hydrogen and an equatorial up hydrogen. There's an axial up hydrogen and an equatorial down hydrogen. There's hydrogen in all those different ones that we're just not drawing. The big group that we have is going to be our methyl. And we have a methyl on each of these that are in different positions. And we need to make an assessment on which of those is going to be more stable. And putting a big group in equatorial is going to minimize the interactions of our 1,3 diaxial interactions. So this hydrogen here is going to have some steric clash, and then there's another hydrogen which is going to be here, which is going to have some steric clash, which is going to not be favorable for putting our CH3 there. If we put it in an equatorial position, it's going to be a lot more stable. So of these two different drawings that we have, our major or our most stable, which would maybe just write the word favored, is going to be our right one, because our big bulky group is going to be in an equatorial position. And we can show that this is favored through our arrows. And for that, we're going to draw a long arrow towards the one that's favored, and then just a short arrow in the opposite direction. And this equilibrium arrow right here is signifying the same thing as kind of like saying this word favored. So overall, these are the two different conformations or our chair structures. And the one on the right is going to be our most stable. Now let's go ahead and look at another example. Let's look at one that actually has multiple different substituents. So let's go ahead and focus on this one here. In this case, we're going to have two different CH3s. That's at the end of a molecule, so that CH3 is drawn. Sometimes we'll explicitly draw it in, but you don't need to. There are also going to be hydrogens here, which are going to be of the opposite conformation. And then all the other ones are going to have hydrogens. So let's go ahead and draw the two different chair flips that are associated with this molecule. Now, let's go ahead and start by just drawing our base chairs before we do anything. So we're going to start by drawing two slanted lines that are going to be offset. We're going to have two more horizontal lines, or two more parallel lines, which are going to be kind of making like these little triangles. And then we're going to go in and we're going to connect them. And then for our chair flip, we're going to do the same thing, but our slanted lines are going to be in the opposite sloping direction. So these are kind of like sloping downwards, where these are sloping upwards. Two more parts to get my kind of triangles, and then connect them. So those are my two different chairs that I have. Let's go ahead and start with one of my methyl groups and put it somewhere. So in this case, let's go ahead and focus on this top methyl. And in this case, I'm going to go ahead and put it in the same position that I did in the last one. And I'm always going to start at that same position because it's just easier. We are going to have two different possible positions. And here, and as always, we are going to define my wedge as being up and my dash as being down. So my CH3 is going to be in my up position, and my hydrogen is going to be in my down position. So I'm going to have an axial up methyl and an equatorial down hydrogen. And that's going to correspond to that yellow, which is going to be this one. Now let's go ahead and grab a different color. Let's go ahead and do green. Let's go ahead and draw where that green CH3 is. That green CH3 is going to be exactly one carbon clockwise away. So I'm going to go clockwise, and that's going to get me down to this bottom part. And that bottom part is going to have two spots. There's going to be an axial and an equatorial. And we're going to need to put our groups here. Now, my CH3 has a wedge, and that wedge means it's going to be in an up position. So that means this equatorial up is going to be my CH3, and then that hydrogen, which is going to be a dash, is going to be my down position, and that's going to correspond to our overall molecule. So I have an axial up and an equatorial up CH3. We see that they're both up because they're both wedges, and those are what we've defined as being up. Now let's go ahead and draw our chair flip. So for our chair flip, let's go ahead and start with the yellow. That is going to move down to this bottom side, and that bottom side is going to have an axial down and an equatorial up position. We know that this CH3 needs to remain up, so we'll have this CH3 and then our hydrogen. Let's grab our color. So here I see that my yellow CH3 was originally axial and it's now equatorial, but remains up. Now, if I go clockwise again, it's going to get to this spot here. This spot is kind of pushing upwards, so I'm going to have an axial up, and then I'm going to have an equatorial down. My CH3 is going to need to be my up, and then my hydrogen is going to need to be my down, because we've defined that as being up. So here I had my equatorial up, and now I have an axial. So all I do is I change from axial to an equatorial, but I keep the same direction. One important thing here is you do not draw wedges and dashes on a chair. That has a very, very different meaning, and it is not going in the plane and out the plane. That axial up and equatorial up, or axial down, equatorial down, that is the direction. So you'll notice that these are all just normal solid lines. We don't draw any wedges or dashes. Now, if I look at these two different structures, we now need to try to determine which of those is going to be the most stable. And to make that assessment, we're going to try to put our biggest group in our equatorial position. If I look here, though, in my very first one, I have an axial and an equatorial. If I look on my second one, my chair flip, I have an axial and I have an equatorial. So they're going to tie. I don't have one that's going to be more stable. So in terms of my equilibrium arrow, what I'm going to do is I'm going to draw two half arrows of the same length, because in this case, we actually don't have one that's actually favored. These actually have the same amount of energetics, and therefore neither of those is going to be one of our major contributors. So those are going to be in equilibrium with each other. Let's go ahead and jump down to one more example. And what we're going to do is we're going to look at a molecule that's going to be remarkably similar. The only thing that we're going to do is we're going to change our second CH3, which is my green one, into a dash instead of the original wedge. So our starting is going to be really similar. We're still going to go in and we're still going to draw our kind of two slanted lines to draw our chair, kind of make a triangle, and then go and connect them. Same thing on my chair flip. So my yellow is going to remain the exact same. So this CH3 up here is going to be the exact same. I'm going to have an axial up CH3 and then an equatorial down. And then in my chair flip, I'm going to have my CH3 and my H. So it's going to remain an axial up and it's going to remain an equatorial up. Those are the exact same as what I'd had above. Now let's go ahead and consider what happens to this CH3 that we have been color coding with our green. Now it's still going to be one position clockwise away. So I'm still going to have this same position and it's still going to have a axial down and equatorial up. That is always going to be the case. If I always think of this bottom carbon, it's always going to have an axial down and it's always going to have an equatorial up. You even look at this chair flip. Axial down, equatorial up. Those are always going to stay the same. The only thing is where are our groups going to be on it? So here I see that my CH3 is now going to be a dash, and dash is defined as being down. So therefore my CH3 is in this structure going to be in a axial position rather than an equatorial. So in our top one, it was originally equatorial. Here I have an axial and an axial for both of my methyl groups. If I look on my ring flip, which is going to be one clockwise away, which is going to correspond to this position, I'm going to have an axial up and an equatorial down. My hydrogen was up in the first, so it must remain up in the second one. And my CH3 was down, down, so it's going to remain down and be an equatorial down here. So in this case, I'm going to have an equatorial and an equatorial. Now, if I consider the stability of these two, my one on my left has two axials, which are going to both have 1,3 diaxial interactions with the hydrogens that are not drawn, where on my second one, I have both of my big groups in the equatorial, and that is going to be way more stable. So in terms of my arrow, I'm going to draw one that's going to be pushing way longer towards my double stable one, and then much shorter towards my double unstable one. So this is going to show that these are not going to be even, and I'm going to prefer or favor my one that is both equatorial. And here you'll see that these two structures look remarkably the same. Only thing that changed was I moved one wedge to a dash, but I have a very different chair conformation. Hopefully now you've had a little bit of practice on drawing some chair structures and thinking about stability. In class, we're going to get a bunch more practice about drawing these and thinking about our stability. But for this, I think that's a good spot to end, and I will go ahead and see you in the next one.